Hello, and welcome to lesson 21 of this introduction to calculus with Wolfram U. The topic for this lesson is optimization. So let's begin with a brief overview of the lesson. So we've learned how to find extreme values, maxima and minima early on, and those have been very useful in applications. Now, we also learned that those derivatives and maxima and minima can be used to do things like maximize profits or minimize costs. So they have quite a few very practical uses. So this lesson will continue the approach learned early on to solve some more optimization problems. So it's just a continuation of all the earlier work, but this time around we'll develop a way for solving optimization problems. So we'll set up a set of guidelines which will help us to solve these problems in a systematic way. Okay, so here are those guidelines. Number one, make sure you understand the problem, perhaps by reading it more than once. Next, make a picture to get an idea of what you need to do in the problem. Next, assign a symbol like capital M to the quantity that is being maximized or minimized, and of course do the same thing for all the other unknown quantities. And now use all the information to set up an expression for M in terms of all the other variables. Now the difficulty is that if you have multiple symbols, then you will need to find relationships so that M is a function of just one variable x. After all, we are doing single variable calculus, so you must have just one variable x on which M depends. And one last thing is find the domain of f. Find out where f is defined, because that will tell you the interval on which you must find the maxima and minima. So the final step, you find the absolute maximum or minimum of f using all that you've learned in earlier lessons. So let's begin with an example. So a farmer has 3,600 feet of fencing, and this farmer wants to build a rectangular field that borders a river, but he does not want to put any fencing on the side touching the river. And the question is, find the dimensional field that maximizes the area. Now the first step, let's do an animation. So here's the area for particular values of x and y. So let's begin by starting all the way to the left over here, and let's play the animation. So you see over here that initially the area increases and then it starts to drop. In other words, your configuration can neither be too thin nor can it be too tall. And in fact, here's a picture you have of the problem. You have the area over here depending upon x and y, the length and the width of the field. Okay, so let's now start solving the problem. So the area is given to be x times y. It's the length times the width. And the problem is you have two variables, so you must eliminate one of them. But then you know that 2x plus y must be the length of the fencing available. After all, y occurs only once. So replace y by an expression involving x, and then the area depends only on one variable, x. Now, the point is that you cannot have the value of x exceeding 1800, because otherwise the area would be less than 0, because that factor will become negative. So the domain of the function is from 0 to 1800. And then finally, let's use the closed interval method, like I'm doing over here, to find the critical point, and then here is the area at that value of x. Now the point is that you only have a single critical point, and at the end points you have either a zero area, which makes no sense, or you have this maximum area over here. So you have a maximum at this value of x over here. So the rectangle should be 9 feet long and 1800 feet wide. Okay, so before going on, we need to talk a little bit about absolute extreme values. Early on, we have mostly talked about local extreme values. The point is that if you have a critical number c for a function, and you find that the derivative is, let's say, positive to the left of it for all values and negative to the right of it for all values, then that value is actually an absolute maximum for the function. And in just the same way, if you have a value c for which the derivative is negative for all values to the left and positive for all values to the right, then you have an absolute minimum. So that's just a slightly more general result than the first derivative test. So we have tweaked that test slightly to find absolute maxima and minima instead of local maxima and minima. So as a very simple example, here's x squared with its derivative 2x, and you see over here that that's the minimum, and to the left the derivative is negative, and to the right it's positive for all values, so you actually have an absolute minimum over here. So as an application, now let's take up the problem of making a cylindrical can that holds 1 liter of water, and you want to find the dimensions that will minimize the total cost of plastic that's used to make the can. Now, if you want to minimize the cost of plastic, then the best way to do that is to minimize the surface area of the can. So here's the can itself. That's the surface area, capital S, radius, and the height. So the formula for the area is just the area of the sides and the two bases. So that's the total area. Now you want to eliminate H, let's say. So remember that the volume, pi r square H, is 1000. After all, you have 1 liter of water. So H is 1000 over pi r square. Having done that, you can now write the surface area in terms of just one variable r, and the domain is just from 0 all the way to infinity. So in principle, you could have any value for r. Now the point is you cannot apply the closed interval method because the interval is infinite. So what we do is we first of all work out the critical numbers. There's just one critical number, but then you note that to the left of that value, you have the derivative being negative, and to the right you have it being positive, so actually have an absolute minimum. Okay, now with that radius, you can work out the height using the solution above, this 5.41926, and that says that the radius should be approximately 5.42 and the height should be approximately 10.84. Okay, so now a problem about distances. So you want to find the point on the parabola y squared equal to 2x, which is closest to the point 1, 32. So that's the distance formula. You have the square root of x minus 1 the whole square plus y minus 32 the whole square for that point. Now, because the point lies on the parabola, you have x equal to y squared over 2 from here. So you plug it back and you get a distance function. Now, I won't worry about the square root sign. That doesn't matter. So you work out the critical numbers and you find there's just one critical number. And if you look at the derivative, you actually see that the derivative is going to be negative to the left of 4 and positive to the right of 4. So you actually have an absolute minimum. So the minimum value will occur when you are at 8, 4, and that's the answer to the problem. Okay, so now on to a business example. So let's say you have a store that sells 300 monitors a week at $200 each. Now, the store finds that for each $10 rebate, of course, the sales go up, so the number of monitors increases by number 30 in a week. Okay, the question is, what are the demand function and the revenue function? And you also want to find the rebate that a store should offer to maximize its revenue. So demand function is just a price per unit. So that's given over here. You have the base price 200 minus the discount that customers get depending upon how many monitors are sold. The revenue function is just the total revenue. That's the number of items times the price per item. So to maximize revenue, you simply find its critical value, which is 450, and then you can actually check quite easily that you actually have an absolute maximum at this value. And the price at this value of X is 150. So now the rebate should be 200, the base price, minus 150, that's $50. Okay, now that's all done manually, but in the Wolfram language, we have two functions, maximize and minimize, which can actually find these absolute maxima and minima for a given range without any effort on our part. So for example, in the earlier case, I could use maximize to get back just the same answer for the revenue. And you can also specify a range, and then you get back the answer for that range. So that's maximize. And similarly, you could find an absolute minimum by using the minimize function. So here's the function, and you want to minimize it between 0 and 2 pi. So you use minimize and you get back an answer. And here is a plot showing that that answer is actually correct. So that dot over here is the point which you have a minimum. Okay, so that's the end of this lesson. So the main point is that optimization is a very important area of applied mathematics. A lot of people spend time just solving optimization problems. Now, to solve problems, the first point is you must try and understand what the problem is. So understand the problem, you draw a picture, etc., and make sure you got all the setup right before you try and solve it. And of course, if you are in business, then optimization is particularly important because you want to maximize your profits. So you need some kind of quantitative way of maximizing profits. There are two built-in functions, maximize and minimize, which are really useful for solving such problems. And the next lesson we'll talk about antiderivatives. But before we do that, do review today's lesson. This is quite a difficult lesson. Make sure you understand all the steps, and then we go on to antiderivatives next time. So thank you very much. I'll stop over here.